Hey everyone, Mr. Kim Singh here, and today we're looking at the integration of exponential functions. So we kind of touched on this when we looked at primitives, right? We're thinking about going backwards. So this process of integration hopefully is a little bit familiar. Remember how we have the derivative of e to the x being pretty special, right? Because when you take the derivative of e to the x, you in fact get e to the x itself, right? So I guess the question is, hey, what's going to happen if I want to go backwards, if I want to find the primitive? Well, as you'd expect, you actually end up with the same thing, right? If I'm saying, okay, I've got e to the x here and I want to take, find the primitive or integrate it, what am I going to end up with? Well, I just end up with e to the x, right? So that's not a particularly interesting result, but it is a result nonetheless. So the integral of e to the x, right, the indefinite integral, is just equal to the e to the x. But of course, when you're taking indefinite integrals, you have to have the constant there as well, right? So that's kind of your first identity or formula. You can think about it like that. So it should be dx with respect to x. Okay, so how do we make this a bit more interesting? Well, what we want to think about is, okay, what happens if I start like putting in values or constants in there? So for example, if I take something like this, if I want to integrate e to the 5x, for example, right? Now, if I start to try and build this intuitively, I will show you the formula in a moment, but if you try and think about it intuitively, like what's going to happen? We know that when we work with exponentials, the powers never change, right? So let's say I'm trying to find what this is going to be. Now, if you think about taking the derivative of something like this, if you take the derivative of this, what you'll end up with is you'll end up with a 5 outside the front here, right? So the idea is we want to kind of address that and undo that. And I'll undo that by dividing by 5 or multiplying by 1 on 5. And so when I do that, and I add my constant in as well, so plus c here, can you see how if I take this function and I differentiate it now, so I take the derivative of this power, I drop it down, and I multiply these two together, that would be 5 times 1 on 5. That leaves me with e to the 5x, right? So this is how we can find the primitive of an exponential function with something that's a bit different there, if it's got a constant in this power as well. So the formulaic way of writing that is, so I've got e to the ax plus b. So now I've got some constant there at the front of x, the coefficient, and I've got some other constant there as well. I can write that as 1 over a e to the ax plus b. And any constants there as well. Again, forgot the dx. Okay, so this is the next kind of identity that we have that we can use to integrate exponential functions. So if I have, again over here, just see what's going on. So in this case, a is equal to 5, for example, and when I want to integrate, I'm just going to put 1 over 5 here, plus our constants, and I can work with that there. All right, should we look at some examples? Here's a couple. So again, let's look at something like this. So integral of e to the 2x, for example. Same idea. I've got my a value being 2 here. So I'm just going to integrate by saying, okay, I'm going to take 1 over a, or 1 over 2 in this situation. Keep the power the same though, e to the 2x plus c. And you can always check by differentiating. So I think the thing you want to be aware of is the fact that because we're working with exponentials, we don't modify the power in any way. In these kind of cases, all you're doing is following this formulaic approach, right? Now let's look at a different one. How about this guy? What changes here now? So e to the 3x plus 2. So you may be wondering, hey, how come the b doesn't really interact with this part when I'm looking at the coefficient of this? And it's because if you think about it, when you're differentiating these, you're taking the derivative and then multiplying it. And when you take the derivative, well, that 2 just kind of goes away. That's why it's almost ignored in this integral form here, right? So again, same idea. All you want to do is identify what your a value is. And in this case, our a value is 3. So I'm going to have 1 on 3 e to the 3x plus 2. We keep the powers the same, plus our constant. Okay. And again, I love these because you can always check whether you got this right. If you just take the derivative of this, you'll see that the 3 and the 1 on 3, they'll divide through, and you just end up with your value of 1 there, which is what we wanted. Okay, when we were doing these like exponential functions, we learned that there are other types of exponential functions as well. Yeah, we learned that we could actually take the derivatives of things like this. So for example, 2 to the power x. This is actually also an exponential function, right? It's just that it's base 2 now. So how would we go about integrating something like this? Have a think. So it may not be immediately obvious, but there was a formulaic approach of actually, let's look at the same idea. How did we derive something like this? That's what I want to approach this with. So to take the derivative of something like this, right, 2 to the x, what we had to do was we had to take ln of this base here and then multiply it by the original function, yeah? So if I'm thinking about kind of reversing this, I want to reverse the process, we want to do the same thing, same idea actually. Like we've put 1 over a here. So what's the new, this is just a constant, but this is just a number. So how do I integrate something of this form? So this general kind of form here, integral of a to the x. Well, it's the same idea. What you're going to do is we're going to put 1 over, not just a now, but you're going to put 1 over ln of a, because that's the thing that's being multiplied here, the base, right? And then we still keep this power here. Yeah. So you can see that these will kind of cancel out, divide through. So this is another kind of form that we can use. So if I've got the integral of 2 to the x, for example, I'll just look at this and I'll say, okay, what's my base? Well, it's 2. So I've got 1 over ln of 2 times 2 to the x. And as well, you still have your constants, right? And we can do this to any kind of base here. I can make this a bit different. I could make this, let's do it a bit differently. Let's go 10 times 3 to the x. Okay. Now you might be wondering, hey, hang on, there's this constant here. What can I do with this? Well, anytime we have a constant, my tip for you is just to kind of factorize it out. Because if you factorize it out, it makes the integration generally a bit easier, and you can use other identities you might have, right? So if I've got something like this, then what I can do is I can say, well, that's just going to be 10 multiplied by, let's use this identity again. So the base is 3, so ln of 3. So it should be 1 over ln of 3. So 1 over ln of 3 multiplied by the original function, so 3 to the x there, plus your constants, right? If you're wondering why the c I've just kind of left outside here, it's because, well, if you kind of left it inside the brackets and you multiplied by 10, you're just going to get another constant anyway. So we generally don't need to write like 10 times c, for example. We just leave it as 10 there, right? Hopefully that makes sense. You can simplify this as well if you want to, but that's integration of exponential functions, looking at like the indefinite integrals. Right? And we can try a few different ones, like they may try and mix a few different exponentials together, so something like this. In a situation like this, again, just use your normal integration rules, right? You can actually integrate things separately. If they're separated by an addition or subtraction, we're allowed to do that. So I can integrate this and then integrate this, right? So let's again use our identities here. So I've got my a value being 2, so that first part is just going to be 1 over 2 e to the 2x. Here you're just going to be careful. You want to respect any negatives and things that are going on here, right? But I've got a negative 1 as my a value technically here, right? So if I use this identity, I'm going to leave that negative there from here, right? So I've got 1 over negative 1 now. Looks a bit strange like that. I'll tidy it up in a second. We keep that function the same, plus our constants. And now I can just tidy this up. So this is a negative multiplied by negative. That's just negative 1, right? So that's just going to be negative 1 multiplied by negative 1. So that's just positive e to the minus x plus c. Okay. Here's one more for you for an indefinite one. So I've got 1 minus x plus e to the x. Okay. So again, same idea. We're just going to look at integrating all of these separately. So here, that's just going to become x because it's a constant value of 1. Then I've got here, this is going to be, well, increasing powers by 1, right? So this is x to the power 1. I can increase it and it becomes x squared on 2. And hey, e to the x. Yeah, this identity did come in handy, right? Don't have to overthink it. That's just e to the x. And then, of course, we have our constants here. Yeah, so that's integration of indefinite integrals, looking at the exponential form.